Hello and welcome to Chemistry 9. Okay, so we've spoken about quite a lot already. I did say I wanted to move into, thinking about kind of more complex ideas, orbitals and Schrodinger and Heisenberg and all this stuff. But I don't want to move on to it quite yet. Actually, I think I still have got some issues I want to address here. Um, And it's still this issue with successive ionization energies. Um, yeah, because I think I need to understand this a bit more, and yeah. And I want to just write down the influences again on ionization energy, um, just to clarify these things in my mind. Um, and I'm just going to review. And I think what I'm going to do for the next from 9 to 11, and then in 12, of course, just going to review everything again. Before I move on to the more complex model. Another reason for this is that I want to start doing some graphing, and to do graphs, that's gonna take some additional things I'm going to need to do. But of course, it'll be very useful for all the subjects really. Graphing is just part of the scientific way. Okay, so the influences the size of the positive nuclear charge. I could do the plus VE, but I think sometimes you have to say in a way, only use these shortcuts when you're very very proficient in the material, because then you can. Uh, so it's kind of the case where so as the atomic number kind of tends to infinity, which of course it wouldn't really do that, but it's going to kind of way you can see it. Um, then obviously the positive nuclear charge is going to um, yeah, is going to increase. Uh, uh, yeah. So as z tends to infinity, uh, um, so does the positive nuclear charge. Uh, hmm. Okay. So yeah. Of course, this is in a world. I suppose this is in a world where you could have any. Well, probably best not speculate on that at the moment. Okay, so the distance from the nucleus is going to affect it as well. Because obviously, you can't do much in the nucleus. There's a strong force in that. You can't do much there. Uh, so F uh, is force of attraction between two objects. Yeah, I tried to just do that. F is force. D is distance between. We've got this inverse law, don't we? Uh, Reciprocal, of course, being a type of inverse. Uh, then is proportional to. I should start using the thing there. I shouldn't be writing that, but I mean, we'll see. We'll see. Like I say, it's one of those things, I suppose. Uh, Inverse square law. Yeah, and I want to try to, I guess, try and include all different kinds of terminology, um, but probably don't mix it up too much. We'll see though. We'll see. Um, no, but um, so F is proportional to the did I really write that to 1 over d squared, and then the inverse squared law. There we go. Yeah, so the attraction decreases, of course, as you move further apart. So you can imagine, you know, if you've got like two people or something, if they're all together all the time, the attraction will be very strong. But if they're thousands of miles apart, it's going to be much weaker. That's a good way of looking at it. So yeah, and remember the shell number. The shell number n is the principal quantum number, and it's a principal, of course, being the you know, sort of like yeah, it's not with the LE there at the end. Principal, you know, it's like number one. It's a principal, the main quantum number. So yeah, I suppose that does sort of signify there might be other quantum numbers, but it's a principal one. Shell number n, principal, and the ionization energies are lower for electrons. Okay, but also we also had to mention the third one, which is the shielding effect. And like I say, I did mention this in 7, I did mention this in 8, but I'm just going to go over it again. Mainly kind of to do the graphing, I suppose, is really the main reason I want to get this graph in. I want to try and get a good graph in. So we'll see how that goes. If we get a nice graph in there, we should be good to go. Like a proper graph. I mean, I was thinking like, oh, should I just draw it out? But no, I can't. It's just too much. It's one thing to draw some things, but you can't draw a graph. You just can't. You need that to be a proper thing with, you know. And I don't fancy using a ruler on my tablet, my Wacom thing here. Field shielding effect by electrons in field inner shells. Yeah, so they repel each other, the electrons, don't they? So they're not interested in each other. Yeah, as you can imagine. So you got these little electrons, you know, and there's the shell. And they're gonna, this guy's going to want to go this way, this guy's going to go this way. For some reason I want to put a little nose in the mouth, but no, I'm not going to do that. So yeah, they repel each other, the electrons, and that's the shielding effect. Electrons repel each other, reducing positive nuclear charge. So all these factors we have to take into consideration. So yeah, so there's that. Now, so they're the main factors here. Now we have this, like I say, it's labeled chemistry 8 tables, but of course this is so what we have to consider here, right? And I can't actually write on this, which I probably should change. I may actually change this at some point, so I can actually write in it and put it in as a picture and put it in paint there. But yeah, so the thing about this, right, is that as I've noticed before, is that the ionization energy is going to massively increase. I mean, look at lithium, right? We start off, we're moving one electron, so we've got 2 1. So the principal, yeah, so we've got 2 1 for lithium, right? So we can remove that 1 in the outer shell, right? And yeah. So basically, those two right in the near the nucleus, those two electrons in the inner shell near the nucleus, they're pushing that one out anyway, right? So that one's already on the way out. That's already being said. That outer electron's already said, get lost, beat it, basically. So so it's not going to take. You don't even need to. You don't even need to be like aggressive with that one on the outside of the lithium because it's already gone. So it's gone just 520 uh, uh, kilojoule moles. Yeah. So yeah, not much energy is needed, and then boom. Once we take out our second electron, though, then we're looking. It's much more unstable, isn't it? So we need to really smash it out because that's the one in the inner shell, and so there's only two electrons there. But of course, the nucleus then is like bringing it all together. It doesn't want to let go of that second one. So boom, it goes up to 7,300. So that is a problem, of course. And it's where we see, and of course that's where we see the increase. Of course, for hydrogen and helium, it's not so much. It's not so much, but there still is a quite big increase if you look in helium. And this is of course how we group all the we group all this stuff. And what we're going to see in the graph is we're going to see this, almost like there's going to be a little curve, and then there's going to be like a step function, boom, upwards as we move towards removing electrons from these shells that don't want the electrons removed. Because think about it. I mean, look. I mean, what fluorine, right? Fluorine is a 2,7, yeah. 2,7. Where's 7 then? Yeah, there we go. So you can see it in fluorine, just like you saw it in lithium there. 2,7. So yeah, we get rid of all those 7. Yeah, we get rid of the first one, the second one. It's going 1680, 3470, 6040. Third one, no problem. 8410. Yeah, it's going up a bit, but not much. Yeah, and then 11,000. Yeah, a little bit. Yeah, 15,200. A little bit more. Little bit more. That's interesting, I guess, isn't it? Actually, wait. So what? Let's look at the difference then. So the difference, and I can't be bothered to work out properly. It's difference 1800. So we've got 1800, and then the difference from 2 to 3 is going to be 26, 24. So 18, 26, 24. I'm just doing the differences here. 24. Again, we've got 26. And then a 42. And then, So what you can see here is that these factors I actually mentioned at the beginning, they're affecting what is going on here, and I think it's mainly the shielding effect, but it could also be the distance, I suppose. And this is I'm kind of almost just waxing lyrical at this point. Obviously, it's not entirely accurate what I'm saying. And then yeah, from the 42, and then we got 152 to 179 there. 27. So yeah, so a bit 18, 26, back and then we've got that big 42 from 5 to 6. That's interesting, isn't it? From 5 to 6. 42 up from 26. I'm not sure how relevant that is. What's 6? 6 is carbon, though. Yeah, it's the thing. It's almost like you just have to work this out, and I could probably watch this in a few years' time. I think, oh yeah, I know why that is now. We'll see though. We'll see. And then 152, yeah, so it's 27, and then we got this huge leap from 179 there to 920, which is 741, isn't it? Yeah. So that's quite a lot. What was that? 741 plus 179 is 941 minus 21, 920. Yeah, that's right. So yeah, so that the big leap there, and then again we're back to little leaps after that. So yeah, so as you can see, and we can see a lot in fluorine, we can see a lot in lithium, purely because they are. Yeah, this is going to tell us a lot about the group elements. Like I just want to look at the. See if I can find a periodic table. I just want to look at it. I might actually be able to find one. Just find a periodic table somewhere. I did want to actually. I want to actually look at the periodic table. Yeah. Here we go. Yeah. So group one. Group one, we've got lithium and sodium. Yeah. So that's cool. And then group two is beryllium, magnesium. We haven't got magnesium there; it's too high. Yeah. Group three is boron. Oh yeah, shit! I forgot. I did this incorrectly, didn't I? I put 4 and 5 wrong. Yeah. I did do that incorrectly. Yeah, beryllium. So beryllium is group two, and boron is group three. So boron, I guess, is the one at 5 there. Yeah, and group 1 and 2 is S block, and then group 3 to 7 is P block. Yeah. Yeah. And transition elements are D block, and lanthanide and actinide is F block. Yeah, lanthanum. Yeah, something I always think of that one. Yeah, and there's actually different ways of displaying the periodic table as well. Interesting, but yeah, I'll have to be to get more visual kind of interesting stuff. But anyway, yeah.